Roll a die. You get a number between 1 and 6. Which number? You can't predict it. The outcome seems random, unpredictable, determined by chance. But it's not random. Not really. If you knew the exact position of the die, the exact force of your hand, the exact air currents, the exact elasticity of the table, if you knew the initial conditions with perfect precision and had enough computing power, you could calculate exactly which number would come up. The die is a deterministic system. The randomness is an illusion created by ignorance. This is classical randomness. It's not fundamental, it's practical. We call outcomes random when we can't predict them, not because they're truly unpredictable, but because the systems are too complex to track. But then there's quantum mechanics. And quantum mechanics says something different, something deeply disturbing. When a radioactive atom decays, the exact moment of decay is truly random, not practically unpredictable, not dependent on hidden variables we haven't measured, fundamentally random. There is no deeper level of description that would let you predict it. Or is there? I'm Leonard Susskind. I've spent 50 years working with quantum mechanics, with determinism, with the foundations of probability in physics, and I'm going to explain why the question is anything truly random. Is one of the deepest, most unsettled questions in all of science. Why quantum mechanics seems to say yes, why Einstein said no, why experiments have ruled out certain kinds of hidden explanations, and why, despite all of this, we still don't fully understand what randomness means at the fundamental level. Let me show you why. Start with classical physics. Newton's laws are deterministic. If you know the positions and velocities of all particles at one time, the laws tell you the positions and velocities at all future times. The universe unfolds like clockwork. Every event is determined by prior events. There's no room for randomness, no room for chance. This is Laplace's demon. Pierre-Simon Laplace imagined a hypothetical intelligence that knew the position and momentum of every particle in the universe and could calculate the future perfectly. For such an intelligence, nothing would be uncertain. The future would be as determined as the past. Of course, we're not Laplace's demon. We can't know every particle's state. We can't do the calculations. So we use probability to describe our ignorance. We say the coin has a 50% chance of landing heads because we don't know the exact initial conditions. But that's epistemological randomness, randomness in our knowledge, not ontological randomness, randomness in reality itself. Classical mechanics is deterministic. Randomness is apparent, not real. Then came quantum mechanics, and everything changed. In quantum mechanics, an unstable particle doesn't have a hidden clock telling it when to decay. A photon passing through a beam splitter doesn't have a hidden variable telling it which path to take. An electron in a superposition doesn't have a definite position until you measure it. The outcomes are genuinely random. The theory gives you probabilities, not certainties. And this isn't because the theory is incomplete. It's because nature itself is probabilistic at the quantum level. Einstein couldn't accept this. He famously said, "God does not play dice with the universe." He believed quantum mechanics must be incomplete, that there must be hidden variables, properties we haven't measured yet that determine the outcomes, that randomness is still just ignorance, even at the quantum level. This was the Einstein-Podolsky-Rosen paradox, the EPR argument. Einstein, Podolsky, and Rosen proposed a thought experiment showing that if quantum mechanics is complete, then particles must have spooky action at a distance, instantaneous correlations across arbitrary distances. Einstein found this absurd. He concluded quantum mechanics was incomplete. There must be local hidden variables restoring determinism. For 30 years, this was philosophy. An interesting debate, but not testable. Then in 1964, John Bell changed everything. Bell showed that if local hidden variables exist, if there's a deterministic explanation consistent with locality, then certain correlations between distant particles must satisfy mathematical inequalities. The Bell inequalities, but quantum mechanics predicts violations of those inequalities, stronger correlations than any local hidden variable theory allows. So you could test it, build the experiment, measure the correlations, see whether Bell's inequalities hold or are violated. The experiments were done, first by Alan Aspect in 1982, then by many others with increasing precision, culminating in loophole-free tests in 2015. The result? Bell's inequalities are violated. Quantum mechanics is right. Local hidden variables don't exist. But there's a loophole, a radical one, superdeterminism. Bell's theorem assumes measurement independence, that experimenters can freely choose which measurements to perform independent of the particle's hidden states. But what if that's wrong? What if the choice of what to measure and the hidden state of the particle are both determined by prior causes in such a way that they're correlated? This is superdeterminism, the idea that the entire universe, including your choices, is predetermined from the Big Bang. The particles and the measurement settings are correlated because everything is part of one giant deterministic system. In this view, the Bell inequality violations don't prove randomness. They just prove the universe is conspiring to make it look random. Free will is an illusion. Your choice of measurement was predetermined. And so was the particle's state. The correlation between them creates apparent randomness without true randomness. Most physicists reject superdeterminism. It's unfalsifiable. You can't test whether your choices are truly free. And it requires cosmic conspiracy. The entire universe's history has to be fine-tuned so that every measurement you make gives quantum mechanical results. It's possible, but deeply unappealing. Still, it's a logical loophole. Bell's theorem rules out local hidden variables, but it doesn't rule out superdeterminism. True randomness remains unproven. This is one of the most profound experimental results in the history of physics. It rules out a huge class of deterministic explanations. It tells us that if you want to restore determinism to quantum mechanics, you have to give up locality, you have to allow faster-than-light influences, or you have to give up realism, the idea that particles have definite properties before measurement, or you have to give up free will, the idea that experimenters can freely choose what to measure. Most physicists accept the result at face value. Quantum mechanics is fundamentally probabilistic. The outcomes are truly random. There's no hidden clockwork underneath. But here's where it gets philosophically strange. What does it mean for something to be truly random? In classical probability, randomness is a model we use for our ignorance. We say a coin has a 50% probability of heads because we don't know the initial conditions well enough to predict the outcome. But the coin itself isn't random. It's deterministic. The randomness is in the map, not the territory. In quantum mechanics, we're forced to say the randomness is in the territory. Nature itself is indeterministic. The electron doesn't have a position until you measure it. The radioactive atom doesn't have a hidden timer. The outcome is objectively uncertain until it happens. But what does that mean? How can reality be indeterminate? How can there be no fact of the matter about which outcome will occur? Some interpretations of quantum mechanics try to restore determinism. The many worlds interpretation says every outcome happens in some branch of the wave function. Nothing is random, all possibilities are realized. You just don't know which branch you're in until measurement happens. Determinism is saved at the cost of an enormous ontology. Pilot wave theory, also called Bohmian mechanics, says particles have definite positions guided by a wave that evolves deterministically. Randomness comes from ignorance of initial conditions, just like in classical mechanics. Determinism is saved at the cost of adding hidden variables and non-local influences. But these are interpretations. They make the same predictions as standard quantum mechanics. They can't be distinguished experimentally, so choosing between them is a matter of philosophy, not physics. Here's what we know for certain. Bell's theorem rules out local hidden variables. If you want determinism, you have to pay a price. Non-locality, or many worlds, or something equally strange. Now let me tell you about something even more subtle. Quantum randomness versus algorithmic randomness. In computer science, a sequence is algorithmically random if there's no shorter program that can generate it. A sequence like 010101 is not random. You can compress it to repeat 01. But a sequence like 0110100011110 might be random if no pattern exists that lets you compress it. Now here's the question. Are quantum outcomes algorithmically random? If you measure a quantum system many times and record the outcomes as a bit string, is that string compressible or incompressible? We don't know. Quantum mechanics gives you probabilities, but it doesn't specify the exact sequence of outcomes. It's consistent with quantum mechanics that the sequence is deterministic and compressible. Maybe there's a hidden pattern we haven't found. Or it's consistent that the sequence is truly incompressible, genuinely random, even in the algorithmic sense. This is a deep open question. Does quantum randomness produce algorithmic randomness? We don't have a proof either way. Now, let me connect this to chaos theory, because chaos creates apparent randomness from deterministic systems. A chaotic system is deterministic but extremely sensitive to initial conditions. Tiny differences in starting points lead to exponentially diverging trajectories. Weather is chaotic, double pendulums are chaotic, turbulent fluid flow is chaotic. Chaotic systems are unpredictable in practice, even though they're deterministic in principle. You'd need infinite precision in measuring initial conditions to predict the long-term behavior. With any finite precision, your predictions become useless after some time, the Lyapunov time. So chaos creates practical randomness from deterministic laws. The system is following equations, there's no true randomness, but the outcomes are unpredictable. This blurs the line between deterministic and random. If a system is so sensitive to initial conditions that no realistic measurement could ever predict its future behavior, is it meaningfully different from a truly random system? From a practical perspective, no. From a philosophical perspective, yes. One is determined by laws and initial conditions. The other is not determined at all. But here's the twist. Quantum mechanics adds genuine randomness to chaotic systems. Even if you had perfect knowledge of a classical chaotic system's initial conditions, quantum uncertainty would limit your measurement precision. And that quantum uncertainty, amplified by chaos, means the system becomes unpredictable faster than in a purely classical world. Quantum mechanics makes chaos worse. The randomness is both practical from chaos and fundamental from quantum mechanics. Now let me tell you about quantum computing, because this is where randomness becomes computational power. Quantum computers exploit superposition and entanglement to perform certain calculations exponentially faster than classical computers. A quantum bit, a qubit, can be in a superposition of 0 and 1 simultaneously. When you measure it, you get 0 or 1 randomly according to the superposition coefficients. This randomness is essential. It's not a bug, it's a feature. Quantum algorithms work by putting qubits in carefully designed superpositions, letting them evolve according to quantum mechanics, and then measuring. The measurement gives you a random outcome, but the superposition is designed so that the right answer has high probability and wrong answers have low probability. Run the algorithm many times, and the right answer appears most often. The randomness is harnessed to solve problems. Is this randomness true or apparent? If quantum mechanics is fundamentally random, then quantum computers are exploiting true randomness. If many worlds is correct, then quantum computers are exploring all branches of the wave function simultaneously, and you just see one random branch. Either way, the computation works. The interpretation doesn't affect the results. But here's something subtle. Quantum computers can generate certified random numbers, numbers that provably didn't come from any deterministic algorithm. This uses Bell inequality violations. The correlations between entangled particles are so strong that they can't be explained by any local deterministic process. So measuring entangled particles gives you random numbers that are certifiably random, guaranteed by the laws of physics, not by computational assumptions. This is called device-independent quantum randomness. It's the closest we can get to proving true randomness exists. And it depends entirely on Bell inequality violations, on quantum correlations that can't be explained deterministically. Now, let me address free will, because this is where randomness matters most personally. If the universe is deterministic, then your decisions are determined by prior causes stretching back to the Big Bang. You couldn't have done otherwise. Free will is an illusion. If the universe is random, then your decisions are influenced by random quantum events in your brain. You still didn't control them, they were random. Free will is still an illusion. This is a dilemma. Determinism seems to rule out free will. Randomness also seems to rule out free will. Either way, you don't have genuine control. Compatibilists argue that free will is compatible with determinism, that freedom means acting according to your desires and reasoning, even if those desires are themselves determined. Libertarians argue that genuine free will requires indeterminism and that quantum randomness provides it. Hard determinists argue free will is simply an illusion. I don't have a solution, but I will say this. The question, is anything truly random, is intimately connected to the question, are we truly free? And neither question has a clear answer. Now let me tell you about something that deeply bothers me. The measurement problem in quantum mechanics. Before measurement, a quantum system is in a superposition. The wave function evolves deterministically according to the Schrödinger equation. No randomness. Everything is predictable. But when you measure the system, the wave function collapses, the superposition disappears, one outcome is realized. And which outcome? That's random. Quantum mechanics only gives you probabilities. So quantum mechanics has two kinds of evolution: deterministic Schrödinger equation when you're not looking, and random wave function collapse when you are looking. This is bizarre. What counts as a measurement? When does collapse happen? Why does measurement behave differently from every other physical process? We don't know. This is the measurement problem, and different interpretations handle it differently. Copenhagen says measurement is fundamental. Don't ask what happens during measurement. Just calculate probabilities and move on. Many world says there's no collapse. Everything is deterministic. The apparent randomness is just your ignorance of which branch you're in. Objective collapse theories say collapse is a real physical process triggered by some condition, maybe when a system becomes large enough or massive enough. Randomness is built into the collapse mechanism. Each interpretation makes the same predictions, so we can't distinguish them experimentally. The randomness of quantum mechanics might be fundamental, Copenhagen objective collapse, or it might be apparent, many worlds, and we have no way to know which is true. Let me end with the deepest question. Is the universe deterministic? Quantum mechanics says no. Bell's theorem rules out local hidden variables, but non-local hidden variables remain possible. Many worlds restores determinism at the cost of infinite branches. Superdeterminism restores it at the cost of cosmic conspiracy. The truth is we don't know. We have a theory that works perfectly and makes probabilistic predictions. But we don't know if the probabilities reflect genuine randomness or hidden determinism. Maybe there's a theory beneath quantum mechanics where randomness emerges from ignorance. Maybe randomness is fundamental Maybe God does play dice. We don't know. That uncertainty is at the heart of physics. We have the most successful theory ever created, and we don't understand what it's telling us about reality. Is anything truly random? Quantum mechanics says yes. Einstein said no. Experiments have ruled out simple answers. The question remains open, and maybe that's fitting. The deepest question about randomness has no definite answer.